చెప్పండి.
నన్ను టీమ్స్ లో యాడ్ చేయలేదు సార్ ఐటీ వాళ్ళు. నేను ఎలా క్లాస్ చెప్పాలి సార్?
వావ్.
సార్ ఏంటి సాగపతి చెప్పారు సార్ యాక్చువల్.
ఎవరికి చెప్పారు?
సాగపతి.
ఆయన అక్కడే ఉన్నాడుగా, ఒకసారి అడగండి.
వెళ్ళాలా? ఓకే సార్.
ఒకసారి వీళ్ళు అడగండి.
Will still be able to work and give you output for unknown inputs. So that's the basic difference. Machine learning, it only learns the system and does the model. Artificial intelligence, it understands the system and can still work if the system has changed a bit. Now I'll give you a basic overview of starting from artificial neural networks, and then we'll see how why we need deep learning. So here actually I wanted to tell you that using machine learning you basically need two different algorithms, one for feature extraction or classification, and then you need another algorithms for regression. So using machine learning, you need one algorithm for classification, there's another algorithm you need to use for regression. But if you're using deep learning or if you're using any other artificial intelligence approach, both classification and the regression can be carried out with a single algorithm in a single run. So that's again gives edge, gives benefits to artificial intelligence techniques over machine learning. But having said that, I'm not telling you that the artificial intelligence techniques are always better than machine learning techniques. Sometimes, depending on the type of the data and the application, machine learning approaches can also give you better accuracies and reliability. So, as I was telling you today, we'll discuss basics of neural networks, go through an example, and then we'll try to find out why we need deep learning. So, we all know that in artificial neural network, what we basically do is we try to create a model of our brain, how our brain works, and so it is a good idea to understand our brain first. Now, the brain is the most complicated thing in this world, but we're still trying to understand the basic entity in our brain that is called neuron, and we'll try and see how the neuron works and can be modeled into mathematics. Fine. Now, our brain basically it has more than 1 billion of neurons. It may not sound large enough, but 1 billion is actually really large. It's like 1,000 and thousands. So it's like really there are many, 10 to the power 10. Now, with so many neurons in the brain, and every neuron is further connected to more than 10,000 neurons. It's like very highly connected, interconnected, and complex thing. There is no other complex thing in the world more than the brain. Now, despite all this, the average brain says that it's very like very big. It weighs only 1.5 kg. And if you talk about the energy consumption, the kind of work your brain does, if you try to get the same amount of work from a computer, it would consume 15 million watts, whereas your brain consumes somewhere between 10 to 15 watts. So it's a difference of the order of 4. Now, basically, your brain has so many neurons, and every neuron, it has few parts, starting from the end part, which is called dendrites, and then moving back. I mean, the dendrites are there to catch the information, to receive the information, and the information is passed through. Okay, I'll go to the next slide. Now, as you can see in this diagram, the dendrites, they collect information, and then the information is passed to the synapse. If the information is important, then it will be given more weight. If the information is less important, it will be given less weight. And then the information is passed to the cell body, which is called soma of the neuron, and then the axons are there to give you the output. In a sense, I have provided one small diagram here to explain what one single neuron out of those 1 billion neurons, one single neuron, what it's doing. It's basically collecting all the inputs, these x1 to x3 and x4. These are the inputs. Now, inputs are attached with certain weights. You know, if there's some information which is important, you would remember it for long. But if there is information which is not significant, you would forget in few hours. So it all happens because of these weights. The size of synapse would decide whether the information is important or not, and then the entire information is summed up. So all these inputs are multiplied by the weights, and then they are summed up, and then the information enters into the cell body, and then the cell body, so the cell body will give you an output, which in mathematics we can model it as if some sort of this information going through some sort of a thresholding function. So here, as you can see, this phi is some sort of thresholding function. What this function is, we'll see in the next slide. Now, for instance, if I ask you to multiply 5, 3, and 2, your immediate answer would be 30. So in the process, I'm sure you have not actually multiplied it, but the answer comes immediately because your brain has been trained. And so whenever the information 532 and the multiplication goes into the brain, it would the brain would multiply it with certain weights and pass through certain function. As in this case, I have this 10 hyperbolic as a thresholding function, and then it'll give you the output immediately. So all we need to do in designing this kind of a neural network, we need to identify what these weight matrices are. So normally when we talk about multi-layer artificial neural network, I'm just going quickly because this is all very basic information and all of us already have it. So I don't have to go into the details. I can simply say that the multi-layer artificial neural network means that we are trying to copy our brain, copy how our brain functions. And the brain also has layer construction. The brain has these neurons, they are arranged on various layers in our brain. So similarly, we also use layers here. So the first layer is called input layer, and then we have the last layer is called the output layer, and whatever in between input and outputs you have, they are called hidden layers because they are hidden between input and outputs. So input layer receives all the inputs, and then the input multiply with the weights and given to the hidden layer. So definitely there's a weight matrix between input and the hidden layer. And hidden layer would process this information, pass it through certain function, and then we'll give it out. And input of hidden layers is again multiplied with some certain to go to the output layer. So definitely there is another weight matrix which lies between hidden layer and the output layer. So we got two weight matrices there. If you have one hidden layer, there'll be two weight matrices, one between input and hidden layer, and the other would be between hidden layer and the output layer. So all we need to do is we need to identify this weight matrix, and then the model is complete. So I mean, those who attended the previous session last year would understand this, that we did develop a simple code in MATLAB, and we've seen how this kind of weights identification of these weight matrices using gradient learning is achievable, and we've seen this code how it runs also. So I'll not repeat again. What I'll try and explain is how these weights are updated. So initially we start when we initiate this modeling, we start random weights. So to start with, the weights are assigned randomly, and later on these weights are changed so that the error in the model output and the data output is minimized. So for instance, as you can see here, there are three inputs. So these three inputs are multiplied with three weights and are given to a neuron. The neuron inside has a thresholding function. This function is basically, if you talk about human brain and how it works. So if you try to model it, it is apparent that the brain function is quite close to sigmoidal function. So the function on top here, as you can, is 1 plus e to the power minus x. It's called sigmoidal function, and it quite closely models how our brain works. So this x enters in here into this function, and whatever is the output will be your function output. Now, for instance, let's say I've got some random weights which are 10.7 minus 8.6 and 0.002. So collectively, the inputs multiplied by the weights would be 21.34, and this 21.34 is plugged into this thresholding function, sigmoidal function. The output would be something like 0.999. Okay. Now we'll see further. For instance, let's say you have such kind of a data set where you got input vector in a 1/3 vector, and then the output is basically binary. Okay. So for inputs as 1.4, 2.7, and 1.9, the output should be 0. Whereas for inputs as 6.4, 2.8, 1.7, the output should be 1. Okay. Now, when you're trying to train this neural network, so basically we work with the data. The data is given to the network, and we try to train. So what do you mean by training the neural network? It's basically we are trying to identify correct weight matrix between input and hidden layer, and a correct weight matrix between output and the hidden layer. So, yeah. First thing that you do is you need to initialize the random weights. Okay, good. So we initialize the random weights. See, my first input was 1.4, 2.7, and 1.9, and the output should be 0. Now, so let's say when I calculate with my random weights, the output comes out to be 0.8. Now the output should be, I mean, this is the output from the model, but if you look at the data, the output should have been 0. So instead of 0, I'm getting 0.8. So there's of course an error of 0.8 here, which will be correct. Now, in order to remove this error, but in order to make this 0, what you need to do, you need to change these weight matrices. You need to correct and repair the matrices as shown here, and then you would be able to get it. For instance, there's another set of inputs which is like 6.4, 2.8, 1.7. The output should be 1. Now, from your model, let's say from the assumed weights that you have, let's say the weight that we repaired from the last observation. Now the model gives you an output of 0.9, but your actual output should have been 1. So there's again an error of 0.1 to be corrected. And how do you correct that error? Once again, you'll have to change the weights and the error can be corrected. Now these are just two instances I've explained, but there'll be, this will be repeated for 1,000 and I don't know, 100,000 times, and then making those slight small adjustments into the weights. Eventually, you'll get a weight matrix which will give you perfect output for unknown inputs even. So if you want to understand how this artificial neural network, it works on the error and how it decreases error, there's a very nice boundary perspective given here. So this will explain you how this weights are changed and accordingly the error is minimized. So with time, as you can see, when you train data, eventually you'll be able to differentiate between the data, and this is how you'll find that your artificial neural network can understand the patterns into the data. Now, basically, this training algorithm of ANN, we call it a dumb algorithm because it will only understand what the data is, and it will understand the pattern in the data and will give you the weight matrices. So, but it really helps us, but we need to make it more intelligent. So, as you can see, we just need one hidden layer even if our function is a non-linear, and we can actually solve many of the existing problems using artificial neural network with just a hidden layer. All we need to do is, of course, there's a set of weights that exist and that can produce the target from inputs, and the entire exercise is to finding them. But I just forgot to add one more thing, that the weight matrices that you find using an artificial neural network is not unique. There can be more than one answers. It is possible that that I am training certain data and coming up with a weight matrix, but there's another person who trained his artificial neural network with the same data again, but maybe his initial points were different, and so he would eventually get a slightly different weight matrix, and this is really possible. Now I'll switch to a math example. So what I'm trying to do here is, if you're still able to see my screen and if you're all with me, I think I have time until today. Still have 45 minutes to go through. Good. Now, in this example, what I'll try and explain here is that we'll be developing one small artificial network, a multi-layer perceptron, to identify the alphabets in English language. So there are 26 alphabets, we all know that. But I'm just explaining you how to identify these letters. So the model that we create, it will be given certain information in binary, and the model will tell whether the binary information, it belongs to a certain letter in English alphabet, with starting from A to B. I'm only considering 16 letters for now, but those who are interested can work on this exercise and can create similar algorithm for the entire 26 alphabets of English language. Now, so as I said, we'll use this neural network to train and recognize the letters of alphabets of English language. First letters are identified using 5x7 template. Now, what I mean by 5x7 template is this. So what I'm doing is I'm taking 5x7 matrix. The the boxes in this 5x7 matrix, they are painted. So those boxes which are colored with black, they can be less. If you talk in terms of binaries, so these black boxes taken as ones, and the empty boxes or the white boxes can be taken as zero. So to represent letter A alphabet, I'm using this 5x7 matrix. Okay, and some of the boxes have been colored. Fine. So the template is 5x7, and then the vector can be stored. So if the 5x7 template, the template 35 boxes, right? So all I need to give information to the computer. The information can be given to the computer in terms of binaries, right? So all I need to give is 35 bits of binary. So if you look at this so A letter can be basically defined as 001, 0001, and so on and so forth. So with 35-bit binary, I'm able to define any alphabet of English language in a 5x7 bit template that I have explained. So what I'm trying to do is I'm trying to create an artificial neural network model which will take input these 35-bit binary and will give me an output in terms of whether the letter is A or P or H or N, whatever. Now, the output, as I said, I've got 16 letters, A to P. Okay, from A till P, there are 16 letters. Now, the computer can only give me an output in terms of binaries. So my output vector becomes a 4-bit binary. So if it is a 4-bit binary, if you convert 4-bit binary to decimal, you'll get 0 to 15. So I've got 16 classifications. Now, the artificial neural network that I'm trying to design takes input as these 35-bit binary and will give you an output with 4-bit binary. So the 4-bit binary would tell me whether the letter is A. If the 4-bit binary as an output I'm getting is 0000, that means it is A. And if it is 1111, that means the output P. Okay. If you have any question, if you don't understand, you can actually stop me in here and I can explain it in a different way. Now, what I'm trying to do here is that the artificial neural network will be trained. So I need to collect a lot of data first. Okay. So for that, I need to switch to MATLAB maybe. For a minute, I'll stop sharing, and then I'll try and share my. Now, you have to tell me if you are able to MATLAB window. Okay. So as you can see my MATLAB window, see that the file I'm working is called try letters. So train a neural network, you first need the training data. So let me create a data first. Because when you start working with this, you would learn more. I'm trying to load a file which is called letters, and when I click here, the workspace we are able to see. In the workspace, I've got target vector and X as the input vector. So input vector, as I'm trying to explain, it goes for 16 alphabets in English language. So the first column is for A, second column is for B, and so on and so forth. The last column, 16th column, is for letter P. Okay. So with 35 binary, I'm trying to define English language letter. So these are the inputs. Now for the outputs, I have again 4 by 16 matrix. So every column, the first column is for letter A, second column for B, third column, and so forth. Why is it? It's because the first column has 4-bit binary, which is 0, 0, 0, 0. So when you convert it to decimal, it will give you 0. So 0 is 0 denotes a alphabet. In the second column, binary is 0, 0, 1. So when you convert it to the decimal, it will give you 2, which means the letter is B, and so on and so forth. So now I have the data. If you just want to see, I've created a small function here to plot the data as well. So when I say that my inputs are like, for instance, when I'm saying that this and 35-bit binary denotes letter A, what I actually mean is that if I plot it, it would look like something 8. Okay. Can you see this? So when I'm plotting the first column in this 35 by 16 matrix, the input matrix, I would see letter A there. If I, for instance, if I'm plotting like the 16th column, I should see a P there. Let's see. Can you see a P there? So basically, I have input. I've created a database for the training of my neural network, and the database consists of inputs in the form of 35-bit binary, and output in the form of 4-bit binary for identification of alphabets. This is true, and if you're able to understand this, the next is we need to in order to create this neural network, we need to identify the weight matrix, and there are 2 weight matrices, one between input and hidden layer, weight matrix between hidden layer and output layer. Now these 2 weight matrices we need to identify, and in order to do so, the first thing that we do is we initialize the weights with some random values. So as you can see, I'm using these random values for weight matrix 1, and then I'm using the similar random values for weight matrix 2. The only thing is their sizes are different. So once I have these weight matrices, say the first weight matrix, because there are 30 inputs.
Similar మీరు చెప్తారా?
And there's one bias as well.
No sir, number 1.
Let's say in my hidden layer I've got 10 neurons. So the size of my weight matrix between hidden layer and the input layer would be 10 by 36. Now,
1, 2, 3, 5, 6
hidden layer and the output layer. Now, because my output is 4.
సార్ సెమినార్ అసైన్ చేసినప్పుడు వచ్చి అటెండ్ అవ్వాలిగా.
And the hidden layer has got 10 neurons. If you consider one bias there, so it's 11.
3
so
start
the size of the weight matrix between the output layer and the hidden layer 4 by 11.
నువ్వు ఏదో ఒకటి చెప్పు.
And these
స్క్రీన్ పీపీటీ ఉందా?
This is W1.
ఇంకా
which is 10 by
చేసినంత వరకు చెప్పమ్మా.
36. Okay. And the other weight matrix is
5 తర్వాత 5 గారు ఎక్కడ ఉన్నారు?
has a size of 4 by 11.
మా 5.
So the weights are randomly
కాలేజ్కి
initiated.
వస్తున్నట్టుంది.
Now next thing is I need to conduct a back propagation algorithm and minimize the error. Okay.
5 కాలేజ్కి వస్తున్నారు.
Minimize the error in
సో
production.
3 మీరే స్టార్ట్ చేయండి.
Error in prediction. So
5 క్లాస్ అటెండ్ అయినా సరే ఈ రోజు ఆవిడ
minimize the error in prediction. What actually you are doing is you are changing these weights, and so the new weights would be obtained. So if you look at this I'm using, this bprop2 is basically a function that I've created to carry out this back propagation training. This x is basically input vector of 35 by 16 matrix. T is the target matrix of size 4 by 16. W1 and W2
స్టార్ట్ చేయండి
as you
అమ్మా.
can see are the
స్టార్ట్ చేయండి
randomly
పర్లేదు.
initiated weights, and then you've got 0.05 there, which is my learning rate. 0.1 is the error tolerance, and number of iterations that I have mentioned is 5000. Okay, so if I just click it, probably it will do the entire training in no time. I mean, bprop2 is basically
అయిందమ్మా.
you won't even realize that I've already done it. You even see kind of RMS error that achieved. And you can actually plot this RMS error and show it to you. You would appreciate how quickly this error has been
It is a technique which is used to transform
reduced
the raw data
from
in
0.5 to
and efficient format. The data have quality if they satisfy the requirements
zoom
of
in.
the intended
So,
user. There
so
are many
initially
factors
the error was
comprising the data
0.5,
quality,
and then
such as
you
completeness,
reduce it to
consistency,
0.05.
believability, and interpretability.
The network trained and the weight matrices that we have are the trained
Major
weight
tasks
matrices.
in data pre-processing are data
If you
cleaning,
take
data
these weight
integration,
matrices
data reduction, and
and,
data transformation.
pass this information for it. Maybe I'm interested
Mainly it works
in
on
finding
three.
out, say,
The data by filling
this
the
was my
missing
input
values,
metric,
smoothing
and the
noisy
first
data,
column
identifying or removing
of
outliers, and
35 by 60
resolving
matrix was for letter
inconsistencies.
A.
How to
Now, if I give this as input, it should give me an output. Should be the output should be for
these
letter
missing
A,
values,
and
how
that
to
means
handle
is the
these
first
missing
letter,
values. Ignore the
which
tuple.
means that the output
Ignore the tuple means this is usually done when the class symbol
binary
is
should
missing.
be, the 4-bit binary should be 0000, because I'd kept 0000 for A and 111 for
This method is not very effective
let's see.
unless the tuple contains several attributes with the missing values.
Here, what
It
do
is
I mean
especially
here
for
is basically
Sir, 1 minute.
this is my input. I mean, the first column in X matrix. It is being multiplied by W weight, which is the weight matrix between input and the hidden layer. Then it is passed through a logistic function, as you can see.
Ignore the
Passed through a
tuple. This is
logistic
usually
function.
done when the
And
class
whatever
symbol
is the output,
missing. This method
this
is
is the
not
output
very
from the hidden
effective
layer.
unless the
To
tuple
be
contains
multiplied
several
by
attributes with the missing
W2
values.
weight
It
matrix
is
again.
especially poor when the
This
percentage of
W2
missing
weight matrix
values per attribute
exists between hidden
varies.
layer and output layer. Okay.
By ignoring the
So
tuple, we do not
output of the
make
hidden layer,
use of remaining
all the
attribute
hidden layers,
values
whatever you're
in
getting,
the
has to be multiplied
tuple.
by W2, and then it
And
has to be
coming
passed
to
through another
filling in the
logistic
missing
function
values manually. It is a
to
technique. In general, this
for
approach
that
is
it will become
time consuming
then it
and
will
may
become
not to be
exact
feasible.
output. Okay.
If the data set is
Now
large
in our case,
with
if
many
you look at this,
missing values.
what is the output?
And next, use a global constant to fill in the missing value.
0000. It's almost 0000.
We replace all missing attribute
If I give
values by the same constant such as
00 input,
any label like
I should be
unknown
getting a
or
letter. I mean,
sign of
if you convert
infinity.
0000 to binary, sorry, from
And fourth
binary
one,
to
use a
decimal,
measure of central tendency for the attribute to fill in the missing value.
if you understand this thing.
For
Okay.
normal,
Binary
in
2
symmetric data
is symbol.
distribution, it means the mean can be used. It means mean of the data.
Binary
While
2
in
is
skewed
symbol.
data
And then you've
distribution,
got
we should
0,
employ
0,
the
0, 0. Okay.
median of the data.
Oh yes.
What is noisy data and smoothing? The term noisy is
Say,
a meaningless
this
data
is
that cannot be
something else.
interpreted by machines.
So the answer
It can be generated due to faulty data collection, data entry errors,
fine.
etc. It can be handled buckets or buckets.
So
Each
when it
segment
is
is
15, the
handled
letter E.
separately.
When it is 0, the letter is A. And then you know the
In this
intermediate
beginning,
values. For
we
instance,
have
what
big
is the
medians
output
and
for
big boundaries.
is
In this,
let's see if I can quickly
these are detected by using clustering, file
I'll try
analysis,
to
duplication
you know
analysis.
fool this
Redundancy is another issue.
training that I've
An
done.
attribute may be
Now
redundant if
instead
it
of
can be derived
exactly
from another
A
attribute or
alphabet,
a
I'm
set
trying
of
to give it
attributes.
something which
These
is
redundancy
close
are
to A.
detected by
Okay.
using
And I'll see
correlation
if my
analysis.
A that I've
Coming to
trained
entity
can
identification
still allow
problem,
this letter
multiple data
alphabet
sources.
binary.
Example, the name,
And this
the
alphabet
two names Bill
is
Clinton
stored
and William Clinton. These two names
alphabet.
looks like a similar. When matching attributes from one database
Next
to
thing
another
I'll
during
do is
integration, special
and find out
attention must
for
be
instance,
paid to the
you
structure
know
of the data.
this
This is ensured